Hey guys, what's up? I hope you're doing great. Back with another video, and in this video we'll be discussing bitwise operations, and it would consist of binary representation, basic operations and tricks, and also bit masking. But this particular part, that is bit masking, won't be covered in much detail. The reason is it's a part of dynamic programming, and I'm just making this course right now for beginners. So if you're someone who has already studied dynamic programming, then you would be easily able to grasp the concepts from this video and apply it over there. But if you haven't, then just study bit masking for now and you'll be able to utilize this later on when you study more concepts. Another thing I wanted to clarify over here is that people were asking that why I'm not uploading the videos now. There was a slight delay of around 3 to 4 days between the last video and this one. The only reason is that the batch I'm teaching of 150 students, they hadn't completed all the problems of maths that were initially uploaded. Hence I was waiting for them to complete the videos so that I could upload the next one. So here we are with the next one now, and let's get started. So let's try to firstly understand what bitwise operations are, or what firstly bits are, right? So for that we'll have to dig a bit deeper, and let's talk about decimal representation first. Only then we'll be able to understand binary representation. So the numbers you see on daily basis, for example, the year 2024, for example, your phone number maybe like 98167, anything, right? So all of these numbers are actually decimal numbers because they are made up of all the numbers from 0 to 9. Like each of this value, let's say this particular value is 2, this is 0, this is again 2, this is 6, this is 7, right? So all these values consist of only the digits from 0 to 9, and there are 10 digits in total from 0 to 9, hence it's called decimal representation. Now let's have a look how we even perceive these numbers. Let's look at a very random number, let's say 867. 7 is said to be at 1's place, 6 is said to be at 10's place, and 8 is said to be at 100's place. So we call it 867. Now over here, if you look, then we can write it as 7 into 10 to power 0 plus 6 into 10 to power 1 plus 8 into 10 to power 2. Then it becomes 800 plus 600, plus 60 plus 7, that gives you 867. So the idea over here is that whatever number you are writing in decimal representation, the very first digit from the very right, that is the very first digit over this over here, that would be multiplied by 10 to power 0. Then the first digit, I'm calling this the 0th digit. Let's say this is the 0th digit. So this would then be first, and then the first digit would be multiplied by 10 to power 1. The second digit would be multiplied by 10 to power 2, or in general, the ith digit would be multiplied by 10 to power I. And let's call this coefficients. Let's call 7, 6, 8 as coefficient. So we can generalize this by saying that it's a summation of, like we are adding all the values, so we can call it a summation. So it's the summation of 10 to power I into b of I, where bi is the digit present at the ith location. Now let's try to extend this particular concept to binary representation as well. So by binary representation, what I mean is that you just have 2 digits. Similar to in decimal representation, you had 10 digits in total, but in binary representation, you only have 2 digits, right? So the 2 digits you are having is 0 and 1. So whatever value you want to represent should be represented in terms of zeros and 1. But over here also, this particular formula remains the same. Only this particular value changes. So it would essentially become summation of 2 to the power I, because now it's binary representations. And over here, the decimal representation said 10. So we'll make it a 2 to the power I into b of I. So essentially, whatever number you're going to write in binary representation is going to be represented in terms of some ones and zeros. So it could be 1, 0, 1, 0, 0, 0. Let's try to understand what the value of it would be. So it's going to be 0 into 2 to the power 0, then a 0 into 2 to the power 1, then a 0 again into 2 to the power 2, then a 0 into 2 to the power 3. Sorry, it's a 1 into 2 to the power 3. Okay, then a 0 into 2 to the power 4, and then a 1 into 2 power 2, 5. Cool. So this becomes 32 plus, or this becomes 8. Rest of all the values are 0. So you can say it's 40. So that's how you perceive numbers written in the binary representation. Now, can all the numbers be written in any kind of representation? There could be a ternary representation as well. There is a binary representation. There also is a decimal representation. So yeah, this can be proven that every number can be represented in any kind of representation. But over here, we'll be only discussing of binary representation. But now the point is, why is even binary representation useful? So if you remember, or if you have learned this, then your system or your computer does not understand anything other than zeros and ones. But now you could ask that no, you are actually storing integers, you are storing float values and maybe like doubles and strings, etc. The fact is that under the hood, your language or the high level language you're using or the compiler or there are multiple modules over there, they are converting all these values into zeros and ones. Right? So maybe you give it a number, like store a number for me that is 8. But your system cannot store 8. It can only store zeros and ones. So at the end, it's going to store 1,000. So this would become 0, 0, 0, and this value is 1 into 2 to the power 3. That would give you 8. So that's how system stores the numbers. And it's obvious that if it's storing all the numbers in this particular format, then any operation you're directly doing in the binary representation, rather than converting it to some other form and then doing operations over it, is gonna be much faster. And hence binary representations become important as a computer science engineer and a lot important as a competitive programmer as well. So I think this is enough for the theory part. Let's also see it in practice. So in this CPP code, what I'm doing is I have a int main function, or I have a main function, and I also have defined a function that is get binary. What it's doing is it's just converting my number into its binary representation. If you want to know how it's happening, so there's a data structure called bitset. The way we can write data into bitset is we firstly define how many bits are there. So I'm telling you that telling the system that it needs to have 8 bits, or the data structure needs to have 8 bits in total. And then we say that, okay, this is the number you're going to store. So I'm saying that you need to store X, and then there's a method that is toString, which I'm explicitly asking my data structure to perform. So it's going to give me a string equivalent of whatever value it's storing. So let's see in this, this is in practice. So we already discussed 8. Let's try that. So for 8, we get 3 zeros. So it becomes 0 plus 0 into 2 to the power 0, 0 into 2 to the power 1, 0 into 2 to the power 2, and 1 into 2 to the power 3, right? So 1 into 2 to the power 3 is 1 into 8. That gives an exact 8 to us. Let's say 16. So 16 should be just the other number. Let's try that out. Yeah. So it's again 1 into 2 to the power 4. That would give us 16. If I do a 15, then all the numbers or the first 4 bits should be set. Let's try that. Yeah, the first 4 bits is set. So our program is working perfectly fine, and we'll definitely use it once we understand other operations on a bit. I think with this, binary representations come to an end, and now we can talk of bit ops, or what are the operations that we can perform on these numbers. So let's firstly enumerate all the kind of operations that we can perform on bits. So the first is AND, the other is OR, a very common one is then XOR. You can also have a left shift, and then you can have a right shift. Obviously this list is not exhaustive, but these are the very basic ones, and knowing this would make your life easier. So let's start with the very first one, that is AND. Now what AND says is that if you have 2 strings, let's say 1 0 0 1 0 1 0, and the other could be like 0 0 1 0 1 1 0. Now what AND says is that AND of 2 strings, or AND of 2 numbers, A and B, let's call it A and B, would result into a number C, wherein the values would be 0 for all the places. Now this is the first place, or the 0th place, this is the first place, this is the second, third, fourth, fifth, and sixth, right? So for all places, the value is gonna be 0, except for those places where both the bits are set. So let's look at the places where both the bits are set. So over here, the first bit is set and the second bit is also set. So it's gonna have a value 1. The other places have a value 0, at least at one of the slots. So its value is also gonna 0. It has a 0 over here. Its value is also gonna be 0. It has a 0 over here. So 0 over here as well. This is also 0. These are zeros. And this is also 0. So it's all zeros, but 1 1. Okay, a single instance of 1, and all the others are zeros. Let's try to quickly understand this in the code itself. So let's say, I'll just give you an example. So 4 can be represented as, okay, not 4, let's say 6 can be represented as 1 1 0. Sorry, 1 1 and a 0 0. So this is basically 2 plus 4 is 6. Now let's take another number. Let's say, how can we represent 12? So 12 can be represented as 1 1 0 0. Let's move a space ahead. Yeah. So basically it is 8 plus 4 is 12. So 12 can be represented like this. But now you'll say that, okay, this string is of length 3, this is of length 4. How are we even gonna AND it? So by default, what happens is that these integers you are seeing have a predefined number of bits in itself. For example, if you're talking of int, then int basically has 32 bits, right? Int has 32 bits. And all the bits that you are not talking about right now, like these 3 bits are something we are analyzing. So all the bits that would be there, like the 29 remaining bits would be set to zeros. Over here also, all the 28 remaining bits would be set to 0. So automatically over here we actually have a 0 which we are not considering right now. We can easily perform a AND on it, and when we'll perform a AND, so this particular bit would be set and the remaining would be unset. So let's see the value that we'll get. So we should be getting a value that would be, this would be 0, this would be 1, this would be 0, and this would be 0. And this precisely is the value of 4, right? So this is 1, this is 2, this is 4. So we should be getting a value 4. Let's try to do that. Let's say our A is 6 and our B is 12, and then C is A, or A AND. This is the symbol for AND whenever you want to do it in CPP or in other languages as well. So A and B should be saved in AND. Now what I can do is I can just print all these values so that you get an overview if the values are correct or not. Okay, so let's say this is A, this is B, and this is C. Let's test it out. Okay, give me a second. Oh, forgot the columns. Okay, let's run this. Okay, so firstly we have a 110 as depicted over here. Then we have 11 and 00, and the answer over here has a single 1 that is right over here that we discussed. And if you see, then the only bit is set which is set in both the numbers. So this is basically the AND operation. I can do it with random numbers as well. Let's say we have some 25 and maybe like 46. I don't know. Let's try test them out. Okay, so over here also you have some numbers, some bits are set and some aren't, but the only bit that's set in both the numbers is the one that is set in both of these numbers. Now let's try a bit different value so that at least 2 bits are set. Let's say 27. So in this case 2 bits should be set in the final answer. Yeah, so over here 2 bits are set now, but both of these 2 bits, for example this bit is set and this bit is set, but what you'll observe it that in both the numbers A and B, the first bit was set and the third bit also set, and thereby in the result also the first and the third bit is set. So that's all about AND. There's a similar other operation that's called OR. So what OR says is that AND was saying that the bit would be set only when both the values are set, right? So if A and B are both having that particular bit set, then the value would be set in the answer too. But OR says that the value can be set if either of the bits are set. Like if the bit is set in A or the bit is set in B, then the output bit would be set. So let's take a small example like 0101 and maybe like 0111. So its OR would be, this bit would be set. Let's call this A, let's call this B. Also this bit also would be set because it's set in B. This bit definitely would be set, and this would be unset because it's not set in either of them. So you'll be getting answer 0111. Let's try something similar. So the symbol for OR is this particular pipeline operator. So once you write it, you can actually test the results. Let's see over here. Okay, so it's getting all the values set. Let's test a different number, maybe 35. So over here you see that the bits wherein at least one of the bits are set. For example, at this particular place is right over here where my cursor is. Over here A was having a bit set but B wasn't, but still the output C would be having a bit set. In this particular example also A was having the bit set, B wasn't, still the answer would be having a bit set. Over here this is having the bit in this is not set but it's set in B, so the answer would be having a set bit. That's how OR works, and yeah, we have tried it and we have received the answer as well. Let's try a bit different thing now, that is XOR. XORs are actually extremely common in competitive programming, so let's discuss XOR also. XOR is almost similar, but what it says is that the value would be set only if one of the bit is set. So by that, what do I mean? Let's say this is A, this is B. So now what it'll do is, for the first bit, or for the first place, it'll check that is only one bit set. No, both the bits are not set, so the answer is 0. For second place also, it's see if one bit is set. So over here, both the bits are set. So even in that case, it will give answer 0. Over here, only one bit is set. That is the bit in A set. So it will give answer 1. Over here also the same trend applies, and over here the bit in A is not set, but the bit in B is set. So over here also we'll get answer 1. Essentially, XOR of two numbers A and B, A or B, XOR. So this symbol right over here is the symbol for XOR. Okay. So what it says is that A XOR B would produce a number C, wherein the bits that is set in only one of the numbers would be set, and all the other remainings would remain unset. Let's test it over here. So as I said, that the XOR can be represented in this format. So C is equal to A XOR B. Now let's test the results. So over here, we are able to see that the bits of A and B were both set for the first place or the 0th place, and hence the answer was having a 0 over that. Also for the first place, the bits are both set. For the second place, both the bits are not set, so answer 0. For the third place, one of the bit is set, so we get an answer 1. For the fourth place, one of the bit is set, so we again get answer 1. And for the fifth place, again one of the bit is set, so we get answer 1. So yeah, that's pretty much it about XORs. Let's move ahead to left shift and right shift, because we said that we are going to discuss AND or XOR, left shift and right shift. So left XOR and OR is covered. Let's move ahead. This is covered, this is covered, this is also covered. So let's move to left shift and right shift now. So what left shift does is that we already said that the numbers can be written in this format, ones and zeros. So left shift says that I'll shift the number by some points to the left. So let's say if this is the number I was having, okay, and as I said that there's a preset number of bits that are always available in the data types you are going to use. So all of them would be populated with zeros. So all of these would be zeros because you're not even focusing on them right now. So what would happen is, let's say you say that let's left shift this particular number by 2 units. So left is this particular side. So all of these bits would get shifted to 2 units to the left. So this would come over here. This would come over here. Similarly, this would come over here. This would come over here. This over here. And this over here. But wait now. Over here now 2 empty boxes are there. So what would we do about them? So what we'll do is that we'll add zeros over here. So we'll get a 0 and a 0 over here. And obviously the starting blocks anyway had a zeros, right? So they anyway have zeros, and a number now is shifted by 2 units to the left. Now what's the importance of this particular operation? Let's say we are shifting a number by x units to its left. So what happens is it gets multiplied by 2 to the power x. The reason that it gets multiplied by 2 to the power x is also trivial, but just to give you an overview of it, the simple reason is that all the numbers can be written as b into 2 to the power I. That is something we discussed when we started with binary representations right over here. So what eventually is happening, that you're left shifting each numbers by some x units, right? So all of these numbers would now become b into 2 to the power I plus x, which can be written as b into 2 to the power I into 2 to the power x. So it gets multiplied by 2 to the power x, because when you are going to summate it, so you can say, okay, x came outside and now it's b into 2 to the power I. So that's how it becomes a number that is multiplied by 2 to the power x. And similarly for right shift as well, same operation follows. So let's write the number over here. Okay, let's write a number that is 1, 1, 0 and be like a 1 at the end. So let's say you just want to right shift it by 1 unit. So what would happen is this would move over here, but so what would happen is this number wants to go at a place which doesn't even exist. So you can say that this is going to become a 0 and we are not even concerned about it, because this is the boundary wherein we are concerned about. So in this particular boundary, this comes over here because we are just right shifting it by 1 unit. This comes over here, this comes over here, and obviously the rest of the numbers would be populated by zeros. So this value would actually be, this is 1 plus 4 plus 8, that is 13. This value is 2 plus 4, that is 6. Now you can also say 13 divided by 2 is 6.5, but where did this 0.5 go? So eventually what is happening is that you're dropping off some numbers, right? And if the number that is gonna get divided now, for example, over here, you're trying to divide 13 by 2, obviously there would be some remainders, so we'll have to ignore it because the remainders were actually the digits that you just moved out of the particular range under observation or under the particular bits that are observed. So they will get removed. So essentially similar to left shift, even in right shift, you can say that if you're right shifting a number by x units, then it just becomes another number y. That would be your initial number, let's say num, divided by 2 to the power x. The reason is exactly similar that we discussed over here. The only difference would be that over here you are doing I plus x, and in this particular example you will be doing 2 to the power I minus x, and then you'll be doing 2 to the power I divided by 2 to the power x. So what would happen is many times you'll be doing multiplications by powers of 2 in comparative programming or even in DSA for that matter. And it's always preferred to use bitwise operations. Let's say you want to have the value of a number multiplied by some exponent of 2. So maybe like result is equal to num into 2 to the power I. Now this is a perfectly valid operation. However, a faster operation would be rest is equal to num, and let's left shift it by I units. So I over here. Now this is the way you write a left shift, and this is the way you write a right shift. Now one of the ways to remember it is that this seems like an arrow that's pointing to the left, so the number would be left shifted. This seems like an arrow that's pointing to the right, and this, so the number would be right shifted. So yeah, this becomes right shifting number by I units. This becomes left shifting the number by I units. And now let's look at the code for this as well. So let's say I have, okay, let's remove this. This is not required now. Let's also remove this. And let's say we have A, and then let's define B as A left shifted by 1 unit. Let's make A a bit simpler, maybe like 6. And let's now print both A and B. Okay, let's see that. And also let's see the value of B. Okay, so this was a and now it got left shifted by a single unit. So essentially this moved here, and this 0 got here, and at the end we actually appended some zeros for the remaining places, and the value is also multiplied by 2 in this case, because 2 to the power 1 is essentially 2, so it got multiplied by 2, and the value is now 12. If we do a 2 over here, then the value we should be getting should be 24. Let's see that. Yeah, so now it got moved by 2 places and the value is 24. Let's take a different number, maybe like 36. So yeah, this is 36. This is 32 plus 4 is 36. So it moved over here. This moved over here. Now the number of units they are moving to the left is 2. This moved 2 units to the left. This also moved 2 units to the left. And the value you are getting is 36 into 4, that is 144. And this is how left shift works. Let's also try the right shift for this. Maybe like let's right shift it by 2 units. That would essentially become dividing it by 2 to the power 2, that is 4. So 36 divided by 4 is 9. Yeah, and we get a 9 over here. Over here, each digit has moved to the right by 2 units. And the final answer is also 9. Now let's try to right shift it by 3 units. Let's see what happens. So now we're getting a 4. And over here, there was a 1 that would have now gone to the very end, which we don't consider, or it has gone outside of the limit of the data structure or the data type. So now this is removed, and this one has been right shifted to this particular place. So we do a 36 divided by 2 to the power 3, that is 36 divided by 8, but 36 is not divisible by 8. So we'll ignore the remainder, and the value we get is actually 4. Cool. So that's pretty much it that you'll require to understand in case of operations. But let's also discuss some tricks now, or where easily you can use them. So a few things you have already learned, that is, instead of multiplying and dividing by powers of 2, multiply or divide by 2 to power I, you can just use a left shift or a right shift. Some other useful operations over here are that, let's say you want to check if a number is odd or even. So one way of doing it, that if your remainder after taking a mod with 2 is 1, in that case the number is odd, else it's even. Now to improve this, you can say if your x and 1 gives you some value, or if your x and 1 gives you a value 1, then it's a odd, else it's a even. Now let's see why this works. Because your x would be represented in a binary format, and at the very end, at the 0th position, it would be having either either a bit 0 or a 1. And with this particular bit, the value it will add would be, let's say, 0 or 1 multiplied by 2 to the power 0. That would be 1, right? So essentially it's gonna add a 0 or a 1. Also, all the numbers now which are remaining to its left could have any value, but they would be multiplied by some power of 2, right? So they would be multiplied by either 2 to the power 1 or 2 to the power 2 or 2 to the power 3. All of these are even numbers. So anything multiplied by even number is itself even. So it cannot contribute anything that is odd to the final answer. And thereby, if the number is odd, like if any number is odd, then the 0th place needs to be set. And that's how you can say even if a number is even or if a number is odd. Now what if I ask you that I'm giving you a particular number and let's visualize it in form of a string. So, or in term of its binary representation, let's say this is the string or the binary representation. And in this, you have to turn off the very last set bit. So over here, if you look at the significance of bits, then this is contributing the least, right? Because this is going to be multiplied by 2 to the power 0, then 2 to the power 1, and it keeps increasing to the very left. So the rightmost bit is called the LSB, or the least significant bit. So over here in this particular string, the LSB is this one, because these are actually not set. So the set bit which is to the very right is this one, or the one which is at the second position. So we'll call it the LSB. So what if I ask you to turn off the LSB? Or essentially you have to give me the answer that would be 1 0 1 1 and then followed by zeros. So this is what I expect you to give. So how can you do this? Now a very easy or very naive way would be that you'll say that, okay, I'm gonna traverse across this list, right? I'm gonna take this list up, I'm gonna traverse across this. And how do we traverse across a list? You can write a easy for loop for this. And no worries, I'm actually going to code this up after we finish with our theoretical part. So let's say we can use a for loop over here, and then we can traverse through all the bits and we'll get our answer. But there's an actually easier way to do it. So I'll say that if you want to turn off your last bit, so the result would actually be num. So num is the number for which we want to turn off the last bit, and num minus 1. Now how does this work? So when you do a num minus 1, what it essentially wants to do is it wants to subtract a value 1 from the entire string or from the entire binary representation. So the way it works is, let's say we had a string like this, 1 0 0 0. So you subtract a 1, right? Now what would happen is that there would be carry over here and it would become a 1. So this would also become a 1 because there would be carry over here now. So the carry would transfer over here. Then the carry would transfer over here. Now this is a 1, this would get turned to a 0 and the carry would get over. This is similar to how you do decimal calculations or calculation on decimal numbers. In that also, if you are subtracting a number A from B, so let's say you are trying to subtract maybe like 76 minus let's say 17. Now in this case, at the first position, 6 is actually smaller than 7. So in that case, what we do is that we say that, okay, this particular number is going to become 16. And from 16, we are going to subtract 7. We'll get a 9, right? And then there's a carry, or you can say there's actually a subtraction from the very left part of it. So your 7 now turns to 6. And then you say, okay, 6 minus 1 is 59. So same concept is also applied over here. This is 0. So in order to subtract 1 from it, you'll have to take a carry from the from its left part. And same applies over here. So what essentially happens is, on subtracting 1, if you're able to see over here, all the bits or all the zeros to the right of the very first one are becoming ones now, right? And the very first one from the right is becoming a 0. It's becoming a 0, and rest of the numbers would actually remain the same. So it would be 1 0 0 followed by a 0 and then triple 1. Now if you AND it with the initial number itself, so if you're gonna AND it with 1 0 0 1 and all zeros, so these numbers would actually become all zeros to the right part of this particular line. Let's say this particular line, all the numbers to the right part of it would actually become zeros, because in this the only bit that was actually set has now become a 0. So this was the only bit that was set. It has now become a 0 over here, and all the remaining bits have now become ones. So essentially there is not even a single position wherein both num and num minus 1 would be having the bit set 1 to the right of this particular line. Hence all the digits become zeros. So the resultant would be 0 0 0 0. And over here, since these are exact same values, so we can copy the exact same values. So yeah, when you do a num and num minus 1, then essentially it leads to a result wherein all the bits from your LSB to the very right are all unset to zeros. I hope that's clear. Now there's another one related to it. So if I say num and tilde of num minus 1, so this is a tilde sign. So if I do this, in that case, you'll get an answer wherein only the LSB would be present. Now what do you mean by only the LSB would be present? For example, this is the number. Now over here, this is the LSB. So essentially, my result would be 0 0 0. This would be still present and then 0 0. Now the proof for it isn't really hard. You can definitely try to Google it up and try to study it. If you're still unable to, then definitely ping me on Discord. Now the reason to give such trivial things as homework or as things that you should do on your own is that no matter what you study, it's always a good practice to get into a habit of searching for resources and trying to understand them, because this is a very underrated skill, and I would really appreciate if you start understanding things by this manner. So these are 3 of the tricks that I actually use. We are going to study about some more tricks, but those are pertinent, so we'll study them in the same lecture but not right over here. So let's firstly talk about when I was talking about that we can actually traverse this entire list. So how do we do that? So let's come over here. That's fine. All right, let's remove this. Let's say we don't have this particular structure with us. Let's remove this function as well. And that sounds good to me. Now let's say I have a num, right? Let's give some value to this num. Let's say it's 353. And as I told you in the beginning that an integer actually has 32 bits. So I want to traverse through all these bits. So I'll say that, okay, current bit is like the 0th bit till the 31st bit. I want to traverse amongst all. And now I have to check if the current bit is set or not. So what I'll do is pay attention over here now, because this part is actually important. Num and one left shifted b times. If this is returning me a non-zero value, that would mean this bit is set. Cout set bit. Else we can say that this is not set. So not set bit, let's say. Fair enough. And let's do a slash n. Okay, let's do a slash n just for more readability. And yeah, that's pretty much it. But let's take a smaller number, because anyway we won't be able to confirm whether it's working fine or not. So let's take maybe like 16 and let's run this. All right, missed a semicolon. Let's put that. Cool. So for 16, it says, so it's starting from the very beginning. It says that, okay, the 0th bit is not set, then the first bit is not set, then the second bit is not set, but the third bit is also not set. But now the 4th bit is set, because 2 to the power 4 is 16, right? So yeah, it predicted it correctly and the algo is working fine. But now comes the question, what's this? Num and one left shifted b times. So if you remember, when we talked about left shifting the numbers, over there I stated that if you left shift a number I times, then it gets multiplied by 2 to the power I. Now over here the number itself was 1. So essentially you are saying that the number you need is 1 into 2 to the power b, right? So, or you can just call it 2 to power b. So over here, you are checking whether the bth bit is set or not. If it's set, this would return a non-zero value. Let's just see it in practice, or let's just look at the way it's functioning. So essentially you're saying that you'll keep a 1 and you'll shift it b times. So let's say these are the bits you are having. Let's just assume these are 32 bits in total. So your 1 would reach over here if let's say and your b was maybe like 3. So initially your 1 obviously is at the 0th position, and now you left shifted 3 positions. So this would be 0, this would be 0, this would be 0. So 1, 2 and a 3, right? So now it says that this is the final number you get. So it's all zeros followed by 1 and then 3 zeros. Now what you're going to do is, now you say that okay, the number that is the other number ANDed by this. So let's say this is your num, and let's say it also has some value 0 0 0 1 0 1 0 0, right? Now you're saying that this particular number and this particular number, if they are yielding a non-zero value, that means that particular bit is set. Now how is that true? Because if this particular bit is set in the num itself, that is the third bit is set, only in that case the answer would be 0 0 0 1 0 0 0, right? So that is non-zero. In all the other cases, your answer would essentially be 0 itself, because as we studied in case of AND, the answer would contain a set bit only if the bits is set in both the places. And since in this particular figure, the bottom figure right over here, in this all the bits other than the specified bit is unset, hence there would be only a non-zero answer if the same bit is also set in the num itself. So that's the way it works, and that's how you can actually traverse across the entire number, or you can traverse across all the bits. Now since we have already studied this part, let's try to understand it a bit more, or are there some more operations which we can perform over here. So let's say I want a number wherein this particular bit is unset. So let's call it res, and I want that the res is equal to num, only that this particular bit should be unset in that. What I can do in that case is I'll say that okay, if I'm coming inside of this block, then this, okay, let's say this bit is set. Okay, now what I can say is that I just want to unset this particular bit. So if you remember, when we XOR two numbers, and if that particular bit is set in both the numbers, it becomes unset, right? So we can use XOR over here. So we can say num XOR 1 left shifted b times. Now what would happen is this would yield a number wherein only one bit would be set, that would be the bth bit, and it would be XORed with num. And also, since we are inside this particular if loop, if statement, that basically means that the bit at the bth location is set for num. So essentially in these two numbers, the bit at the bth location is set in both the numbers, and it would now become unset. Now what if we came over here, let's say this else loop, and since we are over here, this basically means that the bit is not set. Now maybe I want to have a number wherein I want this bit to be particularly set. So let's call it res2, and I want that the res2 should be equal to num, but this particular bit needs to be set in that. So even that's easy for me to do, because if you remember that in case of or the or operation, if there are two numbers and a particular bit is set in either of the numbers, even then the final result contains the bit, right? So we can say one num or 1 left shifted b times. Now over here as well, this would produce a number wherein only one bit is set, that is the bth bit. It would be ORed with num. So the result would be another number wherein all the bits that are set in nums would be set, but also the bth bit would be set. So that's how effectively you can use AND, you can use XOR, and you can use OR. There are more combinations to it. If you want, I'll attach some more resources in the description which you can definitely go through to understand these things in more detail. But this is the very basic overview, and most of the times you'll be working with these things only. Now let's get to the very last topic, that is bit masking, and let's try to understand what bit masking is. So bit masking basically means storing some values in sort of a mask. Now wait, what does that even mean? So let's say you are having some functions wherein maybe you are using a vector of bool or array of booleans. Now this can be used to define states, like maybe you want to check that okay, there are maybe like 20 elements, and you have to check that okay, if the ith element has been processed or not. Now in this case, what you can say is, instead of taking an entire array of boolean, you'll just take a number. Let's call it num. Now in case of a array bool, what you would have done is that if you're visiting a particular number, so you would have done that, okay, array of current is equal to 1, right? But over here, what you can now do is you can say that since since there are only 20 elements and the integer can actually represent 32 bits, if I am visiting the value cur, right, then what I'll do is I'll just say that the mask. So basically I'll define the firstly a int mask, right? And if I'm visiting it, I think because of using a lot of Python, now I'm forgetting to add the semicolons. I hope this is temporary and doesn't really messes up context once I start giving them again. But cool. So we can say that mask is equal to mask or. Now you just want to set the bit that is at the location cur. So you'll say 1 shifted cur times. And yeah, now your mask basically contains the information that technically your array would have contained. And in this way, you are actually consuming a lot less space and also making your program faster. And this is what bit masking even means. Now, most people consider it to be a very hard topic. Like bit masking is considered to be a hard topic, but it isn't. Bit masking becomes hard when you try to solve harder DP problems, because therein you have to analyze whether bit masking can be applied or not. Bit masking as a whole is more or less constrained to these things. Like in most cases, you'll either have to turn on a particular bit, which you can do with the OR operation, or in some cases you might want to toggle the bit. By toggling I mean if it's on then make it off, if it's off then make it on, which you can definitely do via or XOR operation. And in other cases it might be required that you need to check whether a particular bit is on or off. In that case you can actually use AND operation. That's pretty much all you need to know about bit masking. And obviously you'll have to understand DP, or wherever you want to apply bit masking, you'll have to understand those concepts. Only then you'll be able to apply these over there. But as a concept, bit masking is more or less only related to this. Yes, there are a lot of tips and tricks for which I'll put links to some blogs of code forces which you can definitely go through, but it won't be required at this point in time. Once we reach to some advanced level where you actually feel that you are facing problems from bit masking in the context itself, then you can study this in more detail. But for now, whatever you'll actually require in a competitive programming journey up to a decent level has already been covered in this video, and you can always refer to more resources as and when required. Also in the description section, you'll be able to find a document which would contain a lot of problems from BitOps. I expect you guys to try those problems out, and if you face any difficulties, then Discord is always there to help you out. And I'll put the link to my Discord server over there as well. I hope this video was helpful, and if you still have a doubt, please ping in the comment section, or better even just ping on the Discord itself. Cool guys, thanks a lot for sticking to the end. I hope this video was helpful. Bye bye.